All right. I'm not going to go as heavy as I did earlier on this, but grounding or ground, as I mentioned earlier, it's an intentional connection to the earth. All right. It does give us lightning protection. It creates an electrical reference point, and that reference point is what we're going to call zero. So when I say it creates an electrical reference point, I'm really saying that it makes a zero potential, or whatever the earth is. All right. It makes everything else that's touching the earth become the same potential as the earth. So since we're going to call the earth zero, everything else that's grounded is also going to be zero. So if I touch two items that are both grounded, they're both going to be the same potential. They're both going to be zero. I am not going to be a conductor that's going to equalize those items out. All right. Offers protection from ground fault circuits. And this one I have to disagree with a little bit. It doesn't really give us protection from ground fault circuits. In fact, if we had a ground fault, it's the bond that gives us the actual protection. And when we talk about the bond, we're talking about the connection between the main bond, which is the connection between my grounding system and my neutral system. Because we stated earlier that if I only have 5 amps of electricity flowing into the earth, then that's not going to be enough to trip the breakers. So what I have to do is get that ground fault, all right, because electricity is going into the earth when it's not supposed to, so that's a ground fault. What I have to do is get that ground fault back onto the neutral, or the grounded conductor. If I can get it onto the neutral wire, now there's no resistance on that at all. Whatever electricity is available on the system will attempt to flow. Far more than that 5 amps that the earth is going to allow. Far more than 15 amps that the breaker is going to trip off at if I go over 15 amps. Even if that 15 amp breaker is broken, it's going to be far more than the 100 amp or 200 amp main disconnect breaker. All right, we're going to have I really don't know what the number is, but it's far greater than that 200 amps. In fact, it's so much that even if the 15 amp breaker is bypassed or overridden and the 200 amp breaker is damaged and that's not tripping off, there's going to be so much electricity flowing at that point in time that wire is actually going to catch on fire. It's going to burn up. And it sounds like it's dangerous, but in all reality, it's a good thing. Because if it catches on fire, it breaks. And air is a resistor. Air is enough to keep electricity from flowing. If I keep two wires far enough apart, electricity will not flow. If I get them close enough together, we're going to start getting sparks, like lightning. So when we get the air, there's no electricity flowing. But if there's enough voltage to jump the air, then we'll get it to go ahead and flow on there. So what we want to do, is burn that wire up if we can't trip the breakers. I mean, breakers are our number one priority. Trip those, turn the power off, everything's safe. If they're broken or damaged in any which way, we burn that up or break the connection. We don't allow for another person to get shocked or electrocuted. We don't allow for that constant flow of electricity to get heated up and start creating and putting the structure on fire. All right? So grounding does not necessarily give us that protection from ground faults. So that one I kind of want to dispel. Bonding does. All right? So going back to bonding, item to item, makes two things the same potential. All right? I want you to also know what the main bond is. All right? For most city water systems, our main bond is going to be located at the first means of disconnect. So wherever that first main panel is, the first thing that I go ahead and turn the power off on, that's where my bond's going to be. In my home, my disconnect is located outside in the meter panel. So I'm going to have a grounding electrode conductor coming out of that and go into my water pipes. I actually have a secondary ground that goes to a ground rod that's right below it. All right. That doesn't, even though it's tied into my distribution panel, my main distribution panel does not have another bond in it. So my grounding electrode conductors go from the first means of disconnect. In my case, it's outside. Most homes, it's going to be wherever the main panel is going to be located at, and that first main disconnect that's there. The two systems that we're connecting is my grounding system and my neutral system. So that if any wire that comes loose, it's going to energize the case, and I guess I should back up and make up a make-believe object. So let's say we have an electric dryer, all right? That electric dryer has wires that are built into it. If one of those wires that energizes the motors comes loose in there and falls and touches the case or the metal container of that dryer, it's going to energize that dryer, or at least the case of that dryer. Even if it gets stripped free of the insulation and that rubs on the dryer, that's also going to be energizing the dryer, all right? If that dryer has a ground plug, so a 3-prong plug on there, that ground plug is going to be energized. So we energize the case, the ground plug or prong is connected to the case, that's energized. That's going to be energized to the junction box, to all of my conduits, all my plumbing pipes. All those items are connected together. So as soon as I have an energized conductor energize the case, it actually energizes all my plumbing system, all my conduits, all the cases, and everything else that has a ground plug that's plugged into, any grounded outlet. All those items are instantly energized because I have one loose wire touching that. I'm hoping you can see how dangerous that is, and we need to turn that power off as fast as possible to keep everything safe coming in there. So what we need to do, if I need to get that electricity back over onto the neutral. So my main box connects my grounding system to my neutral system. My grounding system will only flow 5 amps, not enough of a flow to go ahead and trip the breakers. So I need to have unlimited flow of electricity or unlimited flow of amperage to go ahead and allow that breaker to trip. All right. So in this situation, we'll talk about bonding, and we'll get into that again, and we'll build a bond in the sub panels how we don't bond. I made a comment earlier about faults. Faults is anytime electricity is doing something that it's not supposed to be doing. So typically with breakers, we're going to have an overload fault. So in here, they're showing that we're putting a 50 amp load or any type of work more than what that breaker is allowed to handle. And if it's a 20 amp breaker and I'm trying to flow 50 amps through it, that breaker should sense that and trip and turn the power off, so now no electricity goes through it. Phase to ground, that only works, and if we follow the power back, wire comes loose, just the way the electric dryer that I may mention, energizes the conduit. As long as that conduit is attached to my box, it's going to energize the box. On the bottom, there's a bar that connects my 2 neutral bus bars, and you'll see a green screw in there. All right. So on the bottom, that green screw actually goes right into the neutral bus bars where that metal's connected to it. It goes through the gray or black plastic insulation. So the insulator is the black plastic so that it separates my ground, my neutrals, and everything, and my energized conductors and my bus bars. It keeps all those separated. And then it keeps going through that all the way into the back of the panel, so it screws into the panel. So if my conduit is energized, my box is energized, that bonding screw is energized, that bonding screw is connected to my neutral bus bar, now my neutral wire is energized. Now I don't have any sort of resistance at all. Whatever's available on the system will attempt to flow far more than that 20 amp breaker, far more than the 100 amp main disconnect. So those should trip right away. And even if they don't, then we're going to go ahead and get a burned up wire, which will actually break the power as well. So the second one is a short circuit, also known as a neutral fault. And I should say the third one going down there. That's a neutral fault. That one's real simple. I take the hot and I touch it to the neutral. I don't have to worry about anything else. I'm trying to flow whatever is available on the system. Again, more than what the breaker, more than the main breaker. Those two will pop, or one of the two will pop. And then if they don't, then the wire will burn up. And then we have a phase to phase. Both of those are considered short circuits. If we're going to have a phase to phase, so hot to hot, that voltage separation is going to be bigger. So the phase to neutral short circuit, that's going to have 120 volts and it's going to create a 120 volt spark. If I have a phase to phase short circuit, that doubles the voltage, doubles the size of the spark where it comes into it, but it's still going to trip the breaker. And that's the big audacious goal. Get the power turned off. Anytime that the electricity isn't going where it's supposed to go, we want that power to turn off as fast as possible. Sometimes we're going to run into houses where they're older homes and they didn't have grounding systems in there. The old outlets were two-prong outlets that came in there. This isn't the best practice, and the drawback with this is many of those three-prong testers we use, we don't really find it. This gives me one of the cases I make for why I like non-metallic cable. When we're dealing with non-metallic cable, for the most part, they're going to have an energized, a neutral, and then they're also going to have a grounding wire in there as well. So if we end up replacing some of these things, then we can still make sure that everything's grounded. Now, will this work if I have a wire come loose and an energized case? Yeah, it will. All right. That will go ahead and get the wire over to the neutral. But in all reality, because the neutral always carries amperage, we said amperage doesn't disappear, and if it's 120, doing something like this is basically the same thing as bonding a sub-panel. We're putting that particular ground and that particular neutral together. And if I have another ground path coming in there, I'm actually inviting amperage on my grounding system, and that we just don't want to do. Not to mention, if somebody wires this outlet up wrong, and they do it in a reverse polarity, and I'm sure that anybody who has experience in this, we run into a lot of outlets that people just don't know that the brass screw gets the black wire or the energized wire, and the silver screw gets the neutral conductor, and the green screw gets the ground. If somebody flips those backwards or disconnects it and reconnects it, now I'm energizing the case of whatever I'm plugging into this outlet. And to me, it's just dangerous, all right? We want to keep our grounds and our neutrals separate everywhere except at that one location and that one location only, and that's our main bond, and that's, again, going to be at the first means of disconnect. A little bit more on outlets here. You should have a rough idea of which slot is which and which screw and how many amps each one is designed and so forth. So the first one on the left, we can see that both slots go straight up and down. All right, we do have the round cave-like one, and the cave-like one is going to be my ground prong or my ground slot that comes in there. So that green screw that's on the bottom left, both of those ground ports, I guess, go to that green screw. It also goes to those metal tabs at the top and the bottom, and those screws that are in the top and the bottom. Those are all tied into the ground system for that particular outlet. So many times, because in conduit areas like where we live here in Chicago, we're not going to run separate ground wires to these outlets. We use the conduit that comes in there. So we really don't make a connection to that ground wire or that green screw on there, because those little plates that are at the top and the bottom, they're screwed into the 1900 box or the outlet box on there. And as long as I have a metal connection, then that outlet will be grounded, plain and simple. The narrow slot on the right-hand side, that's for the energized conductor. If you look at the screws on the right-hand side, you'll see those screws are brass screws that go in there. The wider slot on the left side, that's for my neutral conductor slot, and you'll see the screws on that are silver. So the black wire goes to the brass screw, the white wire goes to the silver screw, and if it was a non-metallic system and I had a ground wire in there as well, then the ground wire would go in there. Now, if you notice, it says off 15 amps underneath it as well, all right? Whenever I have the neutral slot and the energized slot, and they're both going straight up and down, that tells me it's a 15 amp outlet, plain and simple. I take the next one in there, and you can see how it's shaped like a T up in there. So if I have the energized conductor straight up and down, and then I have the neutral slot horizontal, that's for a 20 amp outlet. All right. When I get the T, as we're showing here, that's telling me that it's either 15 or 20. It'll work on either one. I could wire it up to a 14 gauge or to a 12 gauge. And I take that back. I should have only a 12 gauge wire going to those. And you will find that back on a lot of 14 gauges. Going off to the right, even more, we start seeing 240 receptacles. And these 240 ones are going to have the energized conductor slot on a horizontal phase. All right. So that's going to tell me that's a 15 or 20 amp plug, and that's going to be for a 240 volt circuit. The bottom one is kind of a split receptacle, and the bottom one here is designed for a 240 circuit, where the top one is only designed for a 120 circuit that comes in there. So you are going to see some weird and awkward outlets, but I'd like you to be able to determine what's what and what they mean. All right. So again, these are just single dedicated outlets. So the one on the left is going to be our 15 amp. The one on the right will be our 20 amp. And only because we have that horizontal plug. All right. This is probably about the safest way to put a plug on there. What is missing is the actual cover plate that holds the actual outlet itself. Right now we just have a 1900 box. There's supposed to be another plate on there that I could screw the top and the bottom of the outlet on there, but at least they went ahead and they put another ground wire from the outlet to the box on there. And as long as that box and all the conduit going backwards is all connected, then even if I remove that outlet, I am still grounded. All right. Otherwise, if that outlet was loose and free, it wouldn't be grounded. The only way I would be able to ground it is to get those metal prongs touching it again. All right.